Thank you all for coming. Just a few short remarks. One is this is a boot camp. I asked the lecturers to prepare their lectures so that the experts would be bored. It's an opportunity to learn something new. And math is not a spectator sport, so I also, for people giving lecture series, they have made up some homework problems for you. Those are printed out or they're on your inbox, either way. And we're even going to have sessions where we go over those problems. And those are straightforward problems, so you should work on them and learn something outside your expertise. This is the week where you should learn something outside your expertise. So without further ado, I'd like to introduce our first speaker, Laurent Manivel, CNRS and University of Montreal. He's going to speak on geometric complexity theory, first of two lectures.
Thank you. Of course, I want to thank the organizers for involving me in this exciting program. So I've been asked to be very elementary, so I'll try to. So my goal is to try to give you an idea of what geometry can allow to do in terms of complexity theory. So I will essentially not say anything about complexity theory in itself. So that's not my field of expertise. And so I will focus more on a purely mathematical question, which is can we compare the determinant and the permanent? So that's rather the focus of the talk. It will be determinant versus permanent. And really, more precisely, what can we learn from geometry? So this looks like really a purely algebraic problem. So why would it be interesting to use geometry, and what geometry can tell us about this problem? Okay. So why and how geometry? So today I want to give you some background on this question and give you a first result which really improved by geometric tools. And then next time I will try to reformulate the problem in a purely algebraic geometric language and try to understand what could be a strategy to try to answer to this fundamental question. Okay, so let's begin from the start. So the determinant. So you take a matrix, and then by M sub n the space of matrices of size n.
Throw the other pen away.
So n times n matrices.
I just had them put new pens down.
Oh, they're there. These are the new ones.
Let's do this one. Okay. So n times n matrices. So of course you know that the determinant can be just expressed as a sum over permutations. This is the set of permutations of n symbols. Permutations have signs, which are denoted by epsilon sigma. Okay. And you have this very familiar expression. So then the permanent is essentially the same polynomial on the matrices, except that we forget the signs. So even simpler. Just take the product, just take the usual expansion, but you don't care about signs. And so it turns out there's these polynomials which are, at first sight, very similar, should be, in fact, deeply different in nature. So at least, so obviously you can say that this polynomial are the same if you work with a field of characteristic 2. So we will avoid this case, so we'll essentially think in characteristic 0 in the sequel. Okay? So let's work over C. So why are these polynomials really different? Well, first, the determinant is really, as you know, very nice. It's easy to compute. For many reasons. Of course, you know, like line and column expansions, you have all kinds of transformations that allow to compute determinants easily. There have been books and books written about that. But maybe the essential point is that the determinant is really multiplicative. So the determinant of a product of matrices is a product of the determinant. So that's really what allows you to compute it efficiently. You can take a matrix X and multiply by matrices, which will give you some involved operations possibly, but in the end, you control very well the determinant. So, okay, so that's a character. Of the linear group. So that's really what explains, from my point of view, the fact that the determinant is easy to compute. In terms of algebraic complexity classes, it is in polynomial time. The permanent still has some nice properties, so you can still expand to lines and columns. So first, the naive operation you can do for determinants, you can also allow it for permanents. Then, of course, you don't have this multiplicative property. There are some formulas which allow you to compute the permanent more efficiently, but then just by taking the defining formula. So, for example, you have so it will be important to keep track of the size of the matrix. So we denote by perm sub n, the permanent of n by n matrices. Okay, so one nice formula is the following. So you take the sum over all subsets of indices of, so there is a sign which is -1 to the power the size of the complement of the set. And then you take the product over the line index and the product of the sums. So you take for each line only the columns corresponding to the set that you have chosen. So this gives you a nice way to compute the permanent. So you have some efficient formulas, which okay, so you should have something like n squared 2 to the n operations to do to compute the permanent. You're using this kind of formula. So Valiant proved that permanent is hard to compute in the sense which is precise, which is it is sharply hard. And so one of the questions is, can we really distinguish this class from this one, for example, by proving that the permanent is fundamentally different from the determinant. Okay. So how can we prove that the permanent is really hard to compute? So one approach is to try to express the permanent in terms of a determinant. Okay. So if the permanent can be computed efficiently, one way would be to express it as a determinant. Okay, so can we write the permanent as a determinant of, not of x, of course, but something which we define in terms of x, and which would be given by some refinement. Okay, you ask the entries of this matrix to be a fine expression of the entries of X. Okay, so a priori this is, so this should not be possible since permanent is pretty difficult to compute what determinant is. So there is a cost in doing this, which is that we'll need to expand the size of the matrix. And if we compute the permanent of a matrix of size n, maybe you can do that, but a priori for some matrix which will be a bigger size. Cost. M will be bigger than n. And the question is, what is exactly the cost of this operation? So of course, if you try the small values of n, then things seems to be easy at the beginning. So you just have to change one sign and you get the permanent from the determinant. But then things go wrong quite fast. So let me give you an answer for 3x3 matrices. So if you take a 3x3 matrix and you want to compute its permanent, so you can write it as the determinant of the following matrix. So it's not a complicated matrix, but still. Zeros. So you can do it, but first remark is that it's not so obvious. And we had to, so this answer gives you a 7x7 matrix. Okay, and I don't know how to make this better. So it seems we have to increase the size of the matrix in a very strong way.
So is this a theorem that it cannot be done with 6x6 now?
I don't know. Is it?
No, it's 5, 6, or 7.
So it's a theorem it cannot be done by 4x4.
Yeah.
Yeah, so we'll see in the end of the lecture that you can not take a 3 or 4x4 matrix, but 5, 6, or 7. Okay, so we don't really care, actually, but... So what we really care about is what happens asymptotically. So if we take n large, which n are we able to use? Okay, so there is a definition, which is the determinantal complexity. So we call the determinantal complexity. So it can be defined for any polynomial, but let's focus on the permanent. N. So is the smallest integer n, so such that we can write the permanent has a determinant of a matrix with defined entries of size n. Okay, so let's call this determinantal complexity of the problem. Okay, so we've seen that fundamental complexity of perm 2 is 2. Fundamental complexity of perm 3 is at most 7. So what else? So it's interesting to have upper bounds, lower bounds. So questions so far? So I want to give you a proof of the following statement. So it's a theorem that the determinantal complexity of term n is at most 2 to the n minus 1. Okay, so I'll give you a way to express the permanent as a determinant of this hopefully big size. Okay, so the proof comes from graph theory. So that's also one of the interests of the permanent. It's not only it's also a reason why it is so relevant in complexity theory is that it is relevant in graph theory. So it allows to compute certain data associated to graphs. So it's also the case of determinants. So let's see how it works. So I'll give you a few general definitions. So let gamma be an oriented graph, finite graph, an oriented finite graph. Okay, so we have a finite set of vertices, V, a finite set of edges, and then there is the classical notion of adjacency matrix. These are vertices of the graph. And it tells you there is an edge from I to j. You put a 1. If there is an oriented edge from I to j, and 0 otherwise. So this gives you all the information, so it really defines your graph. Okay. And then, so the question is, so what is the determinant of this matrix? What does it express? What is the combinatorial content of the determinant of this matrix? Okay, so we just look at the formula. So we have a sum of all permutations of these quantities, right? 1 sigma 1. N sigma n, so let's n is the size of the graph, so the number of vertices. So how can such a monomial be non-zero? So we need, of course, each of these entries to be 1. So this means there is an arrow. There is an edge from 1 to sigma 1, an edge from 1 n to sigma n. Okay, so for each of our edges, we have, for each of our vertices, we have one edge whose source is this vertex, and we have another edge staggered in this vertex. Okay, going to some. Yes. So in the end, a non-zero monomial. Okay, so we have a series of edges like this. So eventually we will come back. So you see that the non-zero monomial corresponds to what is called cyclic covering. Okay, cyclic covering, let's see what it means. A partition of the graph in this joint union of cycles. Any possibility to split your graph into a disjoint union of cycles like that contributes to a non-zero monomial in your determinant. Okay, so then you have a sign. So here the permanent would be better. It would just compute the number of cyclic coverings. So here you have a number of signed cyclic coverings. That's the result. The determinant of A is the number. It's not really a number, it's better to be. Okay, it's a number of signed cyclic coverings of gamma. Okay. So now we just compute numbers, so we're better interested in computing polynomials. So you can modify slightly the construction. Instead of looking to just an oriented graph, you can consider some weighted graph. Which means that for each edge, we choose a weight, xij. Maybe W, coherent with the usual notations. So you can now replace the adjacency matrix by the matrix of weights. Okay, considering the weight to be 0 if there is no edge at all. And then the result is we have just the same expression, except that we have weights here. So in the end, what contributes to this determinant is again this family of cyclic coverings, but the contribution is the product of the weights.
So, I mean, do you need them to consider can you just then not consider undirected graph? Because, you know, the edge is directed a certain way, you just need to.
Okay, I could also do that for non-directed graphs. It's the same as putting graphs with arrows on both sides. Of course, there are many variants of this kind of things. So in the end, the result is not just number of signed cyclic coverings, but number, so maybe the sum of the weights of the cyclic coverings. And so the idea is now that if we take these weights to be some determinants of some expression, polynomial expression, or something like that, and then we will compute some polynomial. So that's what we want to do for the permanent. So the idea is to one day, I think. So consider the following graph. So the vertices will be the subsets of the n-element set. The vertices so choose an integer n. Where is there something to do, which is this? You have to identify the vertex corresponding to the empty set with the vertex corresponding to the full set. What will be the edges? We will have an edge from S to T. With a weight, which will be xij. If what? So I will be the number of elements in T. And T is required to be the union of S with this integer j, which will be the other index. Maybe it's n equal 3, what would we get? So we start with the empty set. We have 1, 2, 3. So this gives us x1 because this has one element, and 1 because we have added the integer 1. x1, 2, x1, 3. Then we go to 1, 2, 1, 3, 2, 3. So here, for example, the weight will be x2 because this has 2 elements, and 2 because we added 2 from here. Okay, so that's set 1, 2, 3. Which, remember, is the same. The vertex here is in fact the same as this one. So this is the graph. Plus, we need to add some other edges, which are just loops from S to S, or S different from the special vertex. And here the weight is just 1. Okay, so we have these loops. This is the graph.
So your 7 by 7 matrix is a special case of this?
Precisely, yes. So the size of okay, the adjacency matrix has size 2 to the n minus 1. So now we want to compute the determinant. Okay, so we have to find the cyclic coverings of the graph. So how can we have a cyclic covering? So one of the cycle we will include the special vertex. And then the only way to have a cycle for this vertex is to follow the edges by adding one different integer at each time. So we have a different color. So the cyclic covering will be get 1 by choosing a path like that, from top to bottom. So this is a cycle because these two vertices are identified. And once you have chosen this cycle, well, what can you do? Nothing. There's no other possibility if you start from here to come back, because you will be obliged to pass through the special vertex. The only possibility that remains, once you have chosen this path, is to choose the remaining loops. Okay. So this is a cyclic covering, and all the cyclic coverings are like that. Are given by choose a path from top to bottom, and then the loops.
But that, sorry, the middle line from top to bottom is not a cycle, right?
It is a cycle because remember that we have identified
Ah, okay.
the top and the bottom vertices.
Okay.
Okay, so now what it is, the determinant is the sum over. So each time we add an integer, so this is encoded in the permutation, the sequence of these integers. So the weight is exactly the monomial we expect. The loops contribute by ones. And then there was a sign, not to forget. Okay, so the sign, remember this, the cycles contributed by a sign, and the sign contribution of a cycle is -1 to the length of the cycle -1. Okay, so the loop contributes to nothing. And then here we have a cycle of length n-1. So it contributes to -1 to n-2. So the contribution is not always +1, but the point is that it does not depend on the path. So up to a sign we really have the permanent, the Algebraic matrix. And of course the sign we can put it in the determinant by changing a line if you wish. So the straight tail solution. So yes, eventually white, if you express the adjacency matrix for this very graph, you get this expression. Okay, so you know how to express the permanent as the determinant of a big Algebraic matrix. The side is exponential in there. So the question is, can we do better? Can we improve this balance? So one of the main conjectures I should mention the name of Leslie Valiant, is that the determinantal complexity of the permanent cannot be bounded by any polynomial in M. So it was some work to bound the determinantal complexity by its exponential expressions. The question is, can we do better? Can we do much better? Can we get some polynomial? Or is it impossible? And why is that impossible? Can we get lower bounds? What about lower bounds? So it's one of the main challenges to get interesting lower bounds. So the lower bounds we know are really weak. So any questions so far? So I should mention, because it's not completely obvious, that the determinantal complexity of the permanent is strictly bigger than m, at least for n bigger than 2. So I gave this as an exercise in the homework. It's not completely obvious. But for example, the geometry can help. If you want to think of this question geometrically, you can arrive at the result in a rather straightforward way. So maybe it's time to use some geometric tools. So the geometric approach could be to try to, so suppose we have suppose there is equality here, so that you can do what we did for n equal 2, so just change a little bit the matrix to the determinant, and by some miracle you get the permanent. Okay, so if the degrees are the same, so in general we can T to be affine, so if the degrees are the same, we can just take it linear, forget the affine part. It would mean that so we can look at the determinant and the permanent as describing some hypersurfaces. Okay, so there is a geometric locus, so inside the space of matrix, we have a hypersurface given by the condition the determinant equals 0. Hypersurface of singular matrices. So this is a geometric object, so you can try to understand this hypersurface geometrically and wonder, is it really different from the permanent? Okay, because if we have this identity, so you can also look at the same at the permanental hypersurface in the space of matrices, and they are linearly equivalent, which implies that geometrically they really look the same. They are just isomorphic, so they should have the same geometric properties. And that's not the case for many reasons. So what would be relevant geometrically to distinguish the two hypersurfaces? For example, so of course we know the determinantal hypersurface much better than we do for the permanent. Okay, again, because there is this property I mentioned in the beginning, that it is a character of the general linear group. So there's an action of the general linear group that preserves it. And so the structure is very simple from your point of view. This does not happen for the permanent, which is much more complicated. So for example, we can look at the singular locus. So it's better to look at these hypersurfaces inside the projectivization. These are two homogeneous polynomials, so these hypersurfaces are just cones. So I forget about the cone structure by going to factoring out the scalar action. I go to the projective spaces. And then the singular, so we need to do that. So the singular locus is a set of matrices of rank. Well, these are rank small, strictly smaller than n, singular locus. Set of matrices whose rank is at most n minus 2. Okay. And so on. You can look at the set of matrices and its singular locus, which is something which is geometrically natural. Take the singular locus. We get matrices of ranks at less than minus 3, etc. By going to singular loci again and again, I would eventually get the matrices of rank 1. And these are precisely these different singular strata. They are the orbits of the action of the linear group. You can multiply matrices from the left and from the right. This preserves the rank, and the orbits are exactly this. Okay, so we can disprove the possibility of the existence of this transformation T by saying that if these hypersurfaces are linearly equivalent, then they will have the same singular locus, and the singular loci will have the same singular locus, and again and again. So in the end, on the side of the determinant, we get the matrices of rank 1, but on the side of the permanent, we don't. Get something different.
What goes wrong when n equals 2?
Oh, you go directly to matrices of rank 1. This is smooth. There is no singular locus. Okay. Go back to matrices, and they are singular, they are just rank 1. No singular locus.
Is there any chance that you could find a point that's on one hypersurface but not the other? A family of points?
Yeah.
If they're different, then there's...
There should be a point like that.
Well, but I mean, you need to know there is not a linear map that maps one to the other. So if you exhibit one point, that's not.
Okay, so you exhibit one point which has really different geometric properties
Right.
that are preserved by linear equivalence. But that's really, very, very weak. Okay, so we'd like to do much better than that. We have to exclude the possibility to have some polynomial bound. Okay, so we must prove that eventually this is bigger than any polynomial in S. We have to be much more clever. So another geometric property, which is very specific to the determinantal hypersurface, is that it contains big linear spaces. So it's interesting to look at linear spaces, because it's really something very specific to the determinant hypersurface. Contains many big linear spaces. And by the way, it's an old and very interesting question to understand the linear spaces in the space of matrices. It's very far from being, it seems to be very basic, and it's a difficult question, but there are many interesting phenomena, very unexpected facts. So that's something we don't really understand, and that would be very nice to understand better. So many big linear spaces, so you can just look at the, so we take for example one column equal to 0. So it does not really distinguish the determinant from the permanent because this is also contained in the permanental hypersurface. But the point here is that you have this action of the group. So you can just move the linear space by the group, so which means that what does it mean here? Just you have a kernel, you look at all the linear maps which have a given kernel. Okay, so this is a space which I can call K CA1 to say that this line is in the kernel of the matrices of this linear space. Okay, and here we have a big family of such spaces. For each line, you can consider a space of matrices which vanish on this, which define linear transformation that vanish on this line. So this gives again a big linear space, and most of them will not be contained in the permanent. So the big difference here is that we can cover, so by using these spaces we can include any singular matrix, of course. Okay, so we have a family of big linear spaces that will cover the hypersurface. But for the permanent we have also big linear spaces, but that do not cover the hypersurface. So in fact, to get a linear space of this size, you will get to fix one line or one column of zeros, so you have a finite number of these, and it will not cover the hypersurface. Okay, so the point is that what I would like to say in this slogan is that the determinantal hypersurface is very flat everywhere. So geometrically, this is how I would understand this. At each point, you have a big linear space. So the hypersurface is flat in some sense. So we can make it more precise. Okay, so more precisely, take so let's choose any singular matrix. So maybe not any, but one whose rank is exactly n minus 1. Suppose A is a matrix of rank n minus 1. So what is nice here, once again, is that we have this GLN action. This tells us that there is normal form, so up to the action of GLN times GLN, we can suppose that A is just the simplest matrix of rank n minus 1, just one of the diagonals and zeros. And then we want to understand the determinantal hypersurface near this point. So it means that we just add something small. Okay, and see what happens. 1 plus x11, x12, etc. One plus n x minus 1 x minus 1 x and n. Okay, so then what is the Taylor expansion of these determinants? So how can we get degree 1 factors? We have to choose the ones on the diagonal multiplied by x and n. That's the only degree 1 factor we can get expansion. What about degree 2 factors? So we have to choose all these diagonal entries minus 1 and just keep the 1. Okay, so for example, we take the 1s here, except for this one, which we have to multiply by this. Okay, and we have these 2 by 2 minors, this 2 by 2 minor, which will contribute to the degree 2 term. Okay, so we have the sum of the x I, x and n, minus x and I, x and n. For I from 1 to n minus 1. Okay, that's the only degree 2 contributions. So what does it tell us? So of course the linear term is just the equation of the tangent hyperplane of the hypersurface. So this we understand quite well. What about the degree 2 term? So you see that maybe I can rewrite it slightly differently. So I have this x and n appearing everywhere. So it's x and n and the sum of the other diagonal entries. And then we have the products x and I, x, I, n. Okay, so once again, this is the tangent hyperplane. So now the degree 2 part of the Taylor expansion, we see that there is something very special happening. So it's a quadratic form a priori in the n2, n squared entries of the matrix. But the rank turns out to be very small. So you have products of linear form. As a quadratic form, this has rank 2. So we have some factor of rank 2. Each of these factors has rank 2 again. We have n minus 1 of these. So the rank is in fact bounded, in fact equal to 2n. So let's call this QA. It's quadratic form. So this is the way we see that the upper surface is flat. We have a rank which is much, much smaller than the dimension. And now we can use this to compare with the permanent. Because suppose that we can solve our problem, so we can express the permanent as a determinant. So suppose that the permanent of n by n matrices can be written as a determinant of n by n matrix of a affine expression in the entries of x. Okay, so what does it mean? We have this means T defines a map from the space of n times n matrices to n times n matrices. Okay, so we have the determinantal hypersurface, and we really cut it out by the as the geometric picture. We cut it out by the image of T, and the intersection should be the permanent. So if the determinant is flat, is very flat, by cutting by some linear space, you still get some flatness. So to be more precise, if we have something like this, suppose we have a matrix B here, which go to some matrix A. So you just compute the Taylor expansion of the permanent.
So you swap the role of M and
Sorry?
before M was bigger than M.
Oh yes. Sorry, I changed N on N. That's true. So I need to be careful. So now if I want to compute the permanent of something which would be, so let's say y plus b. Okay, so we compute this as a determinant of the image by t, so it should be a plus d plus y. Okay, so a plus the t tilde, which is the linear part. Okay, t was defined, so if I apply t to b plus something, I get a plus something which depends linearly on y. Okay, so I get something which will be linear in y plus so my linear form, my quadratic form QA applied to the tilde of y. Okay, look at the Taylor expansion on the other side. Give me something linear plus, which will be the same, plus the quadratic part of the Taylor expansion of the permanent. Okay, so be careful again. Maybe put the permanent and the determinant. And here the n. And here m. Okay, so now I have this linear transformation, but does not matter if I consider the rank. This does not affect the rank. The conclusion is that the rank of this quadratic form, which depends only on the permanent, is at most bounded by 2n. So now that's this point that we will really prove that the permanent is really different from the determinant. So remember that I mentioned the fact that the permanent hypersurface contains these large linear spaces that make the variety very flat, but these linear spaces do not cover the variety. Okay, so in fact, at the generic point, the hypersurface is not so flat. And so in fact, if you choose, so that's a computation that is not so difficult, but if you choose B is a generic matrix, and you have the surface, then this quadratic form is non-degenerate. So that's really, well, it's a computational exercise. It's not that difficult. So, the exercise, you can do this explicitly. So, this generic statement means that you just have to choose one good matrix and do the computation. If you can do that, you're done. So there is a simple matrix here, is a simple matrix that works. The exercise, check that the quadratic form is non-degenerate. The permanent is really 0, so it's on the upper surface. So what did you deduce? The quadratic form is non-degenerate, it means the rank is the dimension. The dimension is m squared.
So what are the entries of that matrix?
Sorry?
What are the entries of that matrix?
They're all 1. All the entries are 1 except this one, which is 1 minus m. So that the permanent becomes 0. So it makes the computation easy because when you do the expansion by lines and columns, it does not depend so much on the coefficients, so you can do it. So the conclusion is really that in the end, this rank is m squared. So we get a lower bound. That's what we were looking for. That's a theorem which is due to Mignon and Besser, really 10 years ago. That the determinant complexity of the permanent is at least n squared divided by 2. Okay, so in particular, if you take n equal 3, for example, you get at least 5, 6, or 7. This has still to be decided. So this is a very nice result because we've seen that we already had to struggle to prove that the determinant is bigger than n and not equal to it. And here we get something which is much stronger. So this is very nice because this is quadratic, so it was really a breakthrough. The previous lower bounds were just linear. And really what is nice also is that this geometric approach is really elementary and the proof is really easy. Except this computation, which is a bit harmful, but not so much. But still, this is still polynomial, of course. So if you want to approach the variant conjecture, we need to get bounds which are not polynomial, to prove that the polynomial lower bound would do. So we're still very far from understanding it. So last week I will explain different approach, reformulate the problem, and see how geometry can maybe help to go beyond this.
Thank you very much. So we built in lots of time for questions, so feel free to ask any kind of question, especially elementary questions are most welcome, because we have 15 minutes for questions, and we still have a full coffee break after that, so don't be shy.
What's known about the dual variety of this number?
So this kind of computation implies that the dual is non-degenerate.
It's a hypersurface.
It's a hypersurface.
Do you know the degree, for example? Something about this.
So that's something I wanted to mention, which is that the existence of these big linear spaces are due to the fact that they can be interpreted as as a consequence of the fact that the dual is very degenerate. So the dual being the variety that parameterizes the hyperplanes. Maybe I should. Explain briefly what is it. Okay, so suppose you have just, you can do that in general, but suppose we have a hypersurface in some projective space. So you look at the smooth points. Then you have the tangent hyperplane to the hypersurface, which is a hyperplane in projective space. So then, as you know, there is this duality in projective spaces, which is the dual projective space parameterizes the hyperplanes. So we can see these hyperplanes as points in the dual projective space. Okay, so the family of these hyperplanes is called the dual variety. So usually it's denoted x star inside the dual projective space, so put it like this. And you have to be careful because you can have singular points, so you have to take some closure at some point, but that does not matter so much. So you have this interesting geometric object that you can associate to a hypersurface, and you expect that in general all the hyperplane will be more or less different. Okay, so you expect that in general this dual is again a hypersurface. And when this is not the case, this means that the hypersurface you started with has some interesting geometric properties. And it's indeed the case that if you start from the determinantal hypersurface, you don't get hypersurface when you go to the dual variety. In fact, you're very far from getting a hypersurface. Okay, so it's like the characterization of the space of matrices. You take the dual, so it is the variety of rank 1 matrices. See that as a product of two copies of projective space inside. So that the dimension of x is n squared minus 2. And the dimension of x dual, which we would have expected to be the same, is in fact 2n minus 2. So you see we have exactly the same numbers that we got for the ranks. It would be the rank of generically this degree 2 part of the Taylor expansion. This is the rank that we got for the determinants, which is not a coincidence, of course. So we can, so that's indeed something which strongly distinguishes the determinant from the permanent. The determinant has this very small dual variety. If you start from the permanent, the dual is really the hypersurface. Again, in that which we have very few things actually. So maybe I can mention that this is something we use to improve a little bit the result of Mignon-Besser. The consequence of this approach is that the permanent not only has determinant complexity at least n squared divided by 2, but cannot be approximated by polynomials with this determinant complexity. Cannot be approximated. That's slightly stronger statement. Polynomials. Of determinant complexity smaller or equal than n squared. But yes, it's true that we hardly know anything about this dual upper surface, and it's surprising that we finally know so little about the geometry of these two upper surfaces. Even for the determinantal case, it's really astonishing if you think about the linear spaces. There's some phenomenon that really strange that we really don't understand. It seems such a natural question to understand which linear spaces are contained in the determinant. What are the maximal linear spaces of singular matrices?
Let's try to get some more questions. Quinn?
Is it possible to improve this statement if instead of looking at permanent, we look on other polynomials?
That's no, well. I mean, other polynomials which would be relevant for this complexity game. That's what you mean?
But in fact, like in issues that kind of statement that permanent is not included in determinant n squared is kind of exactly the boundary that it gives nothing for complexity theory. So you need to improve it like this. But if you maybe if you can improve it for any other polynomial, it will.
Okay, so you mean permanent is really representative of this sharp P class, and we could possibly find some other sequence of polynomials that would be easier to handle.
Yeah, but is it possible to find other kind of polynomials that it's easier to prove for it, but it's not in the orbit of determinant?
Not that I know. If you ask for any sequence of polynomials, the question is obviously yes. If you ask for polynomials that are relevant to complexity theory, then I don't know.
Go ahead. Sure.
Yes, so is n square what to the best known for the permanent?
Oh, this I don't know. Other people know better than I
My question.
do. For general n. That's for general n. Yeah, and so it's a
Even n equals 3.
Okay. So this theorem, this very nice theorem by Manivel and Laurent is 10 years old. But, there's no improvements.
Can you say anything about higher order invariance? Do you get any more by looking at the next term in the Taylor expansion?
You can say many things about the higher order invariance,
But you don't get a better
but you
bound.
don't get a better.
Is it because we just don't understand it, or it will not give a better bound?
How to say?
Is there anything interesting known about the topology of these varieties, like the permanent and determinant, rather than geometry?
Topology, well, there is a huge amount of works on the topology of these discriminant closed sum. Yes, there is a whole literature about it. For the determinant.
For the permanent,
For the permanent, and not that I don't know. Permanent, as maybe you know that. Not that I know.
Maybe I'll ask one more question. So does the permanent behave generically in the sense if I write down the n factorial terms and I put random coefficients rather than just plus, 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 plus 1, is from this point of view of these, do you expect the permanent to be like the generic polynomial with this support? Behave like the generic polynomial?
Well, that's more or less what is expected from the fact that it represents this complexity.
You say yes, Jay says no.
Depends what you mean by generic.
I don't know, for example, the degree of the dual hypersurface. Do we expect that this attains, so
Yeah.
if I take a generic, if there's some degree of the dual, do you think it's attained?
Yeah.
But
In that case, yes.
You think so? It's more than a feeling?
It's a belief.
It's a belief based on certain calculations in small cases.
So still, the permanent has singularities in China. So it could affect the degree of the dual in some way.
But from the overall complexity, if you take a generic polynomial with n factorial coefficient, its complexity will be 2 to the n log n, whereas the permanent has complexity, an upper bound we know of 2 to the n. So in that sense, permanent is not so generic.
Can you say why we restrict just to affine changes of coordinates? Like maybe if we allow quadratic changes of coordinates, then you get some other bound, but then you can get a better bound. Paying for it by quadratic change is not so bad.
I don't really know.
So if you allow higher degrees, then you can just say determinant 1.0.
That's true.
Of course, but then maybe
If you're
there's
trying to
some
quadratic
range in
entries, for
which
example?
if you allow, for size n determinants, maybe you allow half the degree for your changes of coordinates, or you're sort of trading off a little bit.
Maybe it makes sense. It seems to just make life more complicated.
You can show that you can simulate that with affine changes also. So if you had something with,
Yes,
you can make the determinant slightly bigger, instead of letting quadratic entries, you have affine entries. I mean, I don't know the exact law, but it's polynomial.
I see. So you can
Yeah.
just reduce to just doing affine. Yes.
The different degrees in polynomials, but I'm still
There's a question over there, the last question.
It looks to me like, because of the latest hyperplane theorem, the singular cohomology would also behave well when you restrict. So do we know the small cohomology groups of the determinant or the determinant?
The permanent? No, I don't think so. I don't think anybody has ever computed that. Could be interesting.
Okay, well, maybe now we're cutting into coffee break, so let's thank the speaker again. And we continue at 10:45.